Welcome to the last lecture in the Kami sequence, and today we're going to look at getting more into actually verifying common hardware patterns, and we'll get to a simple processor by the end that does have a non-trivial optimization. I'll start by just reviewing the implementation of the simple pipelining example that we ended with last time, and this will be a good opportunity to ask any questions about the basic Kami model or just this thing as a piece of code before we start looking into proving properties about it. So recall the example we ended with last time was a three-stage pipeline system, and I'll just quickly step through the stages one at a time. The first stage has an internal register called data, and every time this stage gets to run, it enqueues the current data value in a queue going to the next stage, and then it increments its data register. And then, second stage, every time it runs, it dequeues from that queue that the last one was pushing into. It doubles the value and then enqueues the doubled value into a further queue that's feeding into the third stage. So far we have the effect of repeatedly adding one and always doubling the result before forwarding it on. And the third stage contains its own accumulator, which will start out as 0, and at every run of this rule here, we dequeue from that second queue. We increment the accumulator by the data value we just read. We send that incremented value off into the world. This is an output of the system. And then we also save the new value of the accumulator. Any questions at this point about this as the definition of an algorithmic system, or the semantics of the language I'm using? All right. And at the end, I just plug together those three stages with a queue between each pair of stages. And we looked briefly at the not entirely trivial implementation of queues or FIFOs near the end of the last lecture. So that's part of the system definition. It's not a primitive. But here's a much simpler specification that I hope you'll believe me is capturing what we expect the system to do without talking about queues. It's one module with two registers. They actually correspond to registers from different stages of the original pipeline. And there's just one rule: reads the data, doubles it, adds that to the accumulator, and outputs that value, and then saves values back into the accumulator and the data register. So I hope it makes sense why we expect this system to do the same things as the other system, possibly with different timing properties, but in terms of the sequence of values that get output to the external world, it really should be the same, and that's what we're going to try to prove. Any questions about that proposition before we start trying to prove it? All right, better have Coq process that. The first thing I'll do is just get out of the way a bunch of facts about well-formedness of the different programs we've defined. We saw what well-formedness means for this particular variable encoding. The acronym is here, and I pronounce it FOAS. That's what I'll do in this lecture. There's for many different encodings of syntax of programs in Coq, there are notions of well-formedness, and there are tactics that will prove that kind of well-formedness for each of these definitions, and I'll add each of these lemmas I've proved as hints. So at various points in the heart of the proof where we need to know well-formedness, these facts will be picked out of the air and used without bothering us. And there's another property about well-formedness of use of registers, which is an even more boring syntactic property. Let's get that out of the way too. All right, so now we've recorded well-formedness of all the parts of our implementation and our spec. It is time to prove. So this is the relation that we'll use. It corresponds to the notion of refinement that we saw last time for the simple message passing software style language. It basically means any trace that could be generated by running the implementation, any trace of interactions with the world, could be matched by the specification. It is possible the spec could allow some behavior that the implementation doesn't happen to support, but that is okay. That's not the concept of correctness we're working with here. So the goal for this first part of the lecture is to prove this theorem, and I'll be stepping through a sequence of lemmas that'll get us there. So let's just jump into that. First thing I'm going to do, let me open another file and demonstrate something. I'll actually open this file first, FIFO.v. Recall, for instance, this method here, this is the body of a method, an enqueue method for a queue data structure that is not entirely trivial. It involves 4 separate registers and a sequence of operations and some array dereferencing and arithmetic. But this is really meant to implement the straightforward, simple definition of a queue that we know from functional programming. So the first step we'll make in the proof is to replace the fancy optimized queues with simple functional programming style queues, and we'll need to justify this as a refinement compatible transformation. And what I want to plug in instead is, well, first, I can just write these 4 Galena functions that are pretty normal if we just ignore the weird looking type annotations up here. But they are, I have an extra constructor wrapped around Boolean constants. I have a function to test if the list is empty. I have enqueue and dequeue operations and a sort of peek at front operation. These are quite straightforward. They work with lists of unbounded length, whereas in hardware we'll need to commit to finite sizes for any types that we use in our state. And I can actually take these nice Galena functions and package them up inside syntax of Kami methods by using a feature that we call native kinds, which essentially lets you mix deeply embedded syntax of hardware programs with functional programs in normal Galena style that you can just inject in at particular places. And it turns out, with the way the FOAS encoding is set up, the way you inject an arbitrary expression is to use a variable node. Variables of types that are marked as native are represented as arbitrary Galena programs, whereas variables of types that are marked as syntactic are normal variables. So it's kind of a weird little encoding trick that reuses an existing concept. And I won't dwell too much more on that. But now we have this alternative spec-like implementation of queues, which we couldn't possibly synthesize to hardware. It uses lists that have unbounded size. But it's very useful as an intermediate stage in writing down specifications and intermediate versions of a system as we gradually refine them from the fancy implementation down to the point where they clearly match the specification. All right, so let me know if there are any questions about this part or anything else. But for now, let's take it for granted that we will use a library theorem. Which one is it? It's going to be, well, there's a theorem that the actual runnable queue implements the simpler spec. And therefore, we'll be able to show that the system we defined before, which was 3 stages with fancy FIFOs between them, does the same thing as the system with 3 stages, where first I've reassociated module composition with these parentheses, and I've put in a native FIFO between the first 2 stages, where what used to be there was one of the actual runnable FIFOs. And we're going to first prove that this system has preserving behavior from the original, and I prove a bunch of well-formatness properties. And now I want to show that the original implementation I picked correctly implements this other version, which has done reassociation, and it has substituted in a native FIFO for an optimized one. I'll just unfold these definitions so we can see what's going on here. What's the difference between these 2 sides we're trying to relate? Just some parentheses popped up here, and FIFO1 changed into native FIFO1. So I'm going to use lemmas from our framework to guide us towards proving this. I'll use transitivity of this refinement relation, and I'll introduce an intermediate stage that is like the right-hand side, except there's still an actual runnable FIFO in this position as opposed to a spec-like FIFO. So now I get 2 sub-goals to show the refinements between the original left side here and this intermediate term, and then this intermediate term in the original right side. And the notation kind of went away. Pretend this trace refines ID is using the same operator as this. So we'll zoom in on this first goal. We can see the 2 sides of this are the same modulo associativity. So we have a tactic k-similar that knows how to figure out all uses of commutativity and associativity. So that'll just take care of that. And then I need to show that the intermediate term is a refinement of this thing here. And what's different here is, well, now all the parentization is the same, so I can use this k-modular tactic to reduce to proving refinements between all the corresponding positions between the two sides. So I'll run k-modular, and now I need to show this first argument of the plus plus on the left is compatible with the first argument of the plus plus on the right. Well, let's now recurse inside the plus plus operators a little more. I need to show stage 1 refines itself, reflexivity, we have a tactic for that. Now I need to show FIFO1 plus stage 1 refines and FIFO1 plus stage 2. So I'll do another descent underneath the plus plus. And finally here I have to use a theorem that shows that the fancy FIFO implements the specification of FIFOs. This is the only real action in this proof. The other parts are just reflexivity. Oops. So I've now proved this theorem showing that I can reassociate the parentheses and substitute in the spec version of a more realistic implementation. Any questions here? Yeah?
Is there a tactic that will, I guess, sort of like intuition, just unify the parts that are similar and leave you with only subgoals for the parts that are different?
I'm not sure. It doesn't sound too hard to build, but I don't remember seeing it in the library so far. Any other questions here? All right. So what we've done is, I'm going to go through an iterative process, taking the implementation and making it look more and more like the spec, and justifying each change that I make, and then chaining all those together to get that the implementation is correct overall. So this was just the first stage of that. The interesting part of these proofs is about our use of pipelines and how there's a general design pattern of pipelines that is correct. So generalizing what we saw there, let's think about pipelines where there's a function that takes us from one state to the next, as well as an extra function f that we call to format a state for passing on to the rest of the world. And then we can define a big old recursive function that captures the idea that every successive pair of elements in the queue is related by calling the next function, and then the actual outputs that appear directly in this list here are further produced by calling the f function. And then we can get some nice properties like if that pipeline invariant holds for a list like this one that ends in f applied to some value, then we still have a valid pipeline sequence if we additionally add to the end f applied to the next of the value we had before. And also, we can invert the pipeline invariant. It's when you remove from the front of a list, you preserve that invariant. So we'll be able to reuse this in two different parts of the proof that's coming. So, all right, let's think about focusing in on just the first two stages of the pipeline. I want to prove I can merge those together into one, and then I'll use this fact within my larger proof to get to merging of all three stages together into one. Prove some well-formedness. This is the spec I expect for the merged first two stages. It has a data register, and it's just always incrementing and multiplying by 2 in the same rule. Remember before there were two separate rules with a queue mediating between them to have one module do the incrementing and the other module do the multiply by 2. And I'd like to be able to prove that the actual two-stage version is refining the one-stage version, but we'll need a few more ingredients to do that. Does it make sense what we're trying to prove here and why this intuitively should be a correct relationship? All right, so one trick I'm going to use here is the inlining operation that I described briefly at the end of yesterday's lecture. I'm going to find another module that we produce mechanically from the two-stage system by just inlining these modules together, and the combined state of the new system will be the state of the two individual systems we started with. And I can use this tactic k inline refine to compute an element of the set of modules that impl12 refines, and we'll just happen to get out one that is inlined, which means it looks like this. It has two registers, which are exactly the registers of the original system. Note we've now inlined the state of the queue into this combined module. So there's no more separate queue data structure. The two stages and the queue have had their state all smushed together, and now there are two rules corresponding to each of the rules in the original two modules. And we don't have to worry about module composition. Everything is nice and flat here now. Yes?
No registers were being shared between the modules, right? Like the original queues.
The original queues were shared between modules, yes.
But they have their separate registers.
Queues have their separate registers, which are now all incorporated here.
And when we are combining all those registers into one state, are we still, differentiating them? Like
No. All the registers are plopped together in one pile in one module from all the original constituent modules.
But like the data is not being corrupted.
Corrupted.
Like the content that was being stored in the registers.
The registers will have the same content as before. They're just we've just peeled away a layer of modularity, but the content will be the same as before, just rearranged in space somehow.
And even total number of registers are same. Like if
Total number of registers is the same as before, yeah.
I thought that.
All right. So then, let's now prove our property that we can merge the first two stages together. I'll instantiate our general pipeline machinery where the function that computes a next state is just the add1 function, and the function that further formats an output is just the identity function, because remember let's see, we're only thinking about the pipeline between the first two stages, and at that queue, the times 2 effect hasn't been incorporated yet. It's in the next queue where times 2 is incorporated. So then I'm going to define an invariant, and it's a little weird. I'm defining an invariant as a record that inhabits type prop, which is just a convenient way of combining existential quantifiers with a fact that mentions the quantified variables, but where I can have it's kind of easier to invert facts like this, and we have nice names for everything. So this invariant is going to characterize what's always true in the original two-stage system at every step of execution. And I'll need to rely on this invariant. This is a lot like the invariants we were just looking at in Zach's lecture about a distributed system, but written in a different way. So data v is going to be the value of the register called data, and we're enforcing there's a value of the appropriate type there, which is a bit vector of length data size. And else v is going to be the contents of the FIFO, which remember, we already replaced our FIFO with a nice simple spec level FIFO that uses calc lists. So this is a genuine list. And then our pipeline invariant holds of the list that we pulled out with the pending data value added to the end and using the particular next and format for output functions that we chose up there. So this invariant is important. It characterizes the sense in which we're using the queue correctly to compute the true function that we're after. And then I define a bunch of tactics here. For every invariant we're proving, we'll tend to define 3 tactics. This tactic is supposed to do all the forward reasoning that we want. In this case, for instance, we'll find a hypothesis that mentions this invariant and destruct it so that the constituent facts like this one come into the context. This is a backward reasoning tactic when we're trying to, say, prove an instance of this invariant. We'll call eConstructor to switch to proving this fact as well as finding instances of all these here. And then there's just one tactic for when you might want to consider both backward and forward reasoning. So the question, yeah?
Are these tactics defined here really specific to the goal you're about to prove? Or?
Yes.
Okay.
They're specific to this invariant. That's why they're being written custom for each invariant proof instance. And then we'll see how they're used in a moment. So now it's time to prove the invariant. I want to say, assume I have, this is like the transitive closure of the step relation in the last lecture. Assume that I run the inline version of the two-stage system from the initial state, which is actually equal to the initial register values of yada, yada, yada. Then we'll reach state n and generate labels LL. Well, I'll ignore the labels for now. I just want to know any state we can reach in this way satisfies the invariance. And I just do that in this case by induction on the multi-step relation. And I have a tactic here, which is doing some forward reasoning for me, taking apart facts about steps in the Kami language, so we don't have to worry about all the inversion. It just happens for us automatically, and a bunch of other tactics here that I won't dwell on, but this could be fun to poke around after the lecture. Another call to the same tactic here, and then a bunch